Hi everyone, welcome back to Anu's Chem Corner. I am Anu and today we are going to dive into buffers. What they are, how they will work, why they were so important. So if you have ever found buffer confusing, this video is definitely for you. We'll break down all the concept and yeah, definitely I told you titration. For understanding the titration, we need an idea about buffer and salt. Salt, you can check my other video and here we are going with a buffer. Let's get started. Buffers. So what is buffer? How we can simply explain buffer? Okay. For example, if you are taking a 1 glass of water and the pH of water, it's 7. While you are adding some acid to it, what happened to the pH of water? Yes, definitely it will be decreased to some 2 or 3 value, isn't it? So it will be lower, like the pH value now becomes lower than 7. Okay, while you are adding some NaOH, what happened? Definitely, the pH will be increased, right? Now the pH will be greater than the 7, correct? So that's a usual scenario. Okay, suppose you are taking a buffer. So what is buffer? Whatever it is. But the solution called buffer if you are taking and you are they have some X pH value and you are adding some HCl. Do you know what happened? The pH will not change. Okay, it will maintain like X. The X, it's not a neutral. Buffer is usually not neutral. It can be acidic or basic. So you can expect a lower than 7 value or greater than 7 value. So whatever be there, it's just X. So while you are adding acid, what happened? There is nothing happens. Right? While you are adding NaOH, yeah, again, you can see there is no change in that original pH. Okay, so that kind of solution, if the solution is capable of resisting the pH while you are adding HCl or base, or not only HCl, any acid or base, that is what we called buffer. Okay, then the question is, what is this buffer? Which solution is acting like a buffer, right? So buffer you can simply explain like or define, it's a mixture of weak acid as well as its conjugate base, or you can consider like a mixture of weak base and its conjugate acid. So both kind of buffers are available. Acidic buffers are there and basic buffers are there. Clear? Okay. For example, if you are taking some acid like HF, and which is the conjugate base of HF? Conjugate base means you just remove one H plus, correct? So the resulting species is F minus. So a mixture of HF and F minus is behaving like a buffer, right? Or in the other way, NH like a weak base, for example, you can consider like NH3 and their conjugate acid means, yes, this time conjugate acid you need. So you can just add one H plus. So the species will be NH4 plus. So the mixture is what we call, this mixture is what we called and that buffer. Okay. And while I discussed this topic with my students, like some of them are asked with why all weak acid cannot be act like a buffer, isn't it? Did you also feel like that? Why? Because what their doubt is HF. So HF is actually it's always in equilibrium state, right? So they have some H plus plus and F minus thing. So whenever you are taking just HF, there will be F minus, correct? Correct. All the weak acid, what's the problem? This equilibrium is exist. So all the weak acid when you are taking, there will be weak acid and its conjugate base. Even you are not separately taking F minus, the F minus is there. Then why we can't say all the weak acid itself is behave like a buffer? Do you know why? What's the reason? Because HF, weak acid means suppose it's 100 HF is there, the dissociation is very low. For weak acid, maybe less than 5% is there, right? Most of the ice table we are considering like less than 5% rule. So which means very low percentage only they were ionizing. So we can see some 100 HF you are taking some 5 F minus F minus is only be there, right? So in effect our mixture contain some 95 HF and some 5 F minus, isn't it? Because 5 HF is dissociated like H plus plus and F minus. So see the mixture ratio. 95 HF and just 5 F minus. So that's why the buffering activity is not that much of strong, right? It's negligible buffering activity. Because if the buffer can be act like a buffer, they have to be equal, right? Approximately they have to equal. If high, like full equal thing, that's the higher activity. That's the ideal or optimum condition of buffer. So in this kind of scenario, very low percentage dissociation only, it can result by a weak acid. So definitely the conjugate base quantity will be very, very low. At that kind of time, it can't be act like a buffer. Clear? So that's why just weak acid, we can't say it's buffer. Okay. So always you need to support, you need to add some extra F minus. So HF is there and you are adding some extra F minus. Suppose you are taking some NAF. So NAF will give some F minus. So yeah, that will contribute some F minus in the reaction mixture so that you can consider like a buffer. Okay. So I hope you understood. So that is the buffer thing. So anyway, it's a mixture of weak acid and its conjugate base or weak base and its conjugate acid. Okay. The specialty we also told they are resistant to change in pH while you are adding acid and base. Now the question is how it's possible, why they were doing so. Like even you are adding the acid, why they are not changing their pH, correct? So let's crack that one. So for example, if HF, and again I'm taking HF and F minus as the buffer. So at any acid base, there is an acid part, correct? Any buffer, there is an acid part. And here, this is the basic part. Like conjugate base means it's typically a base, weak base, correct? Okay, let's see. Suppose you are adding some HCl, okay, to this buffer. Do you know what happened? While you are adding an acid, the basic part of the buffer will react with them, which means who's the base here? Is it HF or F minus? Definitely you got it. That is F minus, correct? So basic part of the buffer will react with this acid. So what happened? F minus is reacting with them and the formed species are HF and Cl minus. So see, so the added HCl now it's not there. Added HCl now it's transformed like HF and Cl minus. So will they contribute anything to pH? See what are the formed species? Cl minus is a neutral salt, right? We study like neutral ion. It's a neutral ion. It's formed from a strong acid. Since it's formed from a strong acid, we know that the conjugate base will be negligible, right? If you have any doubt, you can also see my salt video. Okay, so Cl minus is negligible, so they will not contribute to anything to the pH, correct? And what about the formed HF? HF is actually a weak acid, so they can contribute, definitely they can contribute to the pH, like they can change the pH. But in this case, HF is not a new for them, correct? HF have some activity, like HF have some pH contributing thing. They can affect the pH if it's a new thing. But here what's the problem? HF is not a new, right? HF is already there in the buffer. We are already took the HF. So HF activity or their contribution is already there in the mixture. Got it? So HF is not new for them. Okay, for the buffer, while you are adding HCl, the HCl now is not in the picture. HCl is completely dissociated and they were formed H plus and Cl minus, and that H plus is not in that mixture. Why? Because that H plus is now reacted with the F minus and formed HF, correct? So the added H plus is now converted like HF. HF is a weak acid, so that is not that much of contributing to the pH. Some effect is there, but that effect is not new for them. Their original pH is actually because of this HF effect, correct? So that's why I'm telling HF is not new for them. HF is not that much of contributing to the pH in this case. Okay, so the added H plus is completely transformed to HF and Cl minus. So that's why there is no change in pH. Okay, if there is a free H plus, then only they can affect the pH on the mixture. Here there is no free H plus, correct? The only thing is HF, they can't contribute that much. Clear? So that's why there is no change in pH. Okay. So let's see what about NaOH or any base is added to them. If base is added to them, what happen? Yes. Base is added, the acidic part of the buffer. Who is the acidic part of the buffer? Yes, HF is this time. Correct? HF will react with them. So while adding HF, what happened? Sorry, while reacting with HF, what happened? What are the formed species? NaF and H2O. Correct? So see, again, H2O is neutral, right? They are not contributing to the pH. And Na plus is not contributing to the pH because it's a neutral ion, right? And what about F minus? F minus is again a weak base, correct? It's a weak base, but again I'm telling that is not new for them. Weak base F minus is already there in the reaction medium. So their effect is already counted. Nothing new is formed in this reaction, right? If NaOH is added, if there is a change in pH, definitely some OH minus have to be there. But what happened? The added thing, the OH minus is reacting with the H2HF and formed H2O. Okay, and the F minus is also not contributing that much because F minus is a weak base. Yeah, they can do, they are reacting with the water and they will offer some OH minus and HF. But the problem is what? This effect is already counted. F minus is not new for them. That's why they got some original there on pH. Okay, so that's why there is no change in pH. Okay, then see the same we can explain by using this graph. So what is this one? Here we are starting with the same amount of Ha and A minus, which means our acid and the weak acid and the conjugate base, correct? Okay, and you are adding H plus. See, as I told you, acid when you are adding, base part will react with them so that A minus will be decreased. At the same time, Ha will be produced. So Ha will be increased, correct? And what happened when base is added to them? Acid part of the buffer will react with them. So Ha will be decreased and A minus will be increased. Okay. So the ratio, one is increasing, the other one is decreasing. So the ratio will change actually, but the problem is like, if this is 5 and this is 7. So 5 maybe if it is increasing like 10 and this one is decreasing. So it's again like a higher change is happening, right? They were telling does not increase very much. No, it's actually changing, but the problem is their logarithm or their ln value. When you taking the ln of this ratio, it will be very low. Okay, so what is the ln of this ratio means? What's their important means? That is Henderson-Hasselbalch equation. Because in buffer case, we can use the Henderson-Hasselbalch equation for counting the pH. For example, pH is equal to pKa plus log base concentration over acid concentration. This is the equation. Okay, this is what we called Henderson-Hasselbalch equation. You can also use POH is equal to pKb plus log acid over base. That is also correct. Okay. So in this case, see what happened? pKa is always a constant because for weak acid there will be a Ka value. Their negative logarithm will always a constant, right? So when this ratio if it's changed, then pH will also be changed, correct? So as long as this log of base over acid remains the same, pH is also remains the same. That's the thing. That's why I'm telling log of this base over acid ratio while you are considering this reaction. Log, ratio is actually wrong. Log of Ha over A minus does not increase very much or decrease very much. Got it? That's why the thing is not changing the pH. Okay. So this Henderson-Hasselbalch equation is very, very important. Okay. Correct. Then the important point is buffer capacity. What do you mean by the buffer capacity? Definitely, as the name implies, buffer capacity means how much they can be tolerant. Like how much tolerance is there? Like how much HCl or acid or base they can accommodate without changing the pH, isn't it? That's the buffer capacity. So our aim is to prepare a like high or buffer capacity, isn't it? Right. For example, what do you think? Suppose you are taking a 10 mole of HCl, okay? And what you have is 5 mole of HF and 5 mole of F minus, okay? So while you are adding 10 mole of HCl, is it behave like a buffer or not? Like, will it be changed the pH or not? Okay, let's see the equation. Okay, what I'm told, HCl will react with the base F minus, so they form HF and Cl minus, correct? So this is the normal equation. So here initially before reaction what we have 10 mole and F minus what we have F minus 5 moles, correct? So after the reaction, see this is 5 only. So HCl will react with them and this is the limiting reagent at this time. So after the reaction this is 0 but this is 5. So in this reaction there will be 5 mole of HF and 5 Cl minus as well as 5 HCl also be there. Correct? 5 extra HCl is there. Why? Because this is the excess reagent. So definitely the pH will change. Correct? Because 5 mole of HCl we can't omit the presence of HCl. If HCl is there, definitely they will change the pH because they suddenly dissociate like H plus plus and Cl minus. So the effect of H plus will change the pH. Okay? So which means 5 mole of, see, 5 mole of HF, sorry, 5 mole of HF minus mixture can accommodate only 5 mole of HCl. If you are adding 10 mole of HCl, there is no buffer capacity. They can accommodate maximum 5 mole of HCl. Without changing the pH, they can accommodate only 5 mole of HCl. Okay, so 5 is this buffer capacity. Clear? Okay. If it's so, how to improve the buffer capacity? What you call the ideal buffer, isn't it? From this point of view also you may get the idea, like if you want to accommodate 10 mole of HCl, definitely you need to take 10 mole of HF and F minus mixture, isn't it? At that time you can accommodate all the 10 mole of HCl. So yeah, that's the first point. Take the large quantity of buffer mixture, isn't it? If you want to accommodate more acid or more base, you can take more amount of that mixture. Okay, so that should be the first point. And definitely while you taking the thing first, as I told you, the very first point, the ratio of base over acid should be 1. Correct? Because you know the Henderson equation, pH is equal to pKa plus log base over acid concentration. So this ratio determine everything. Correct? So if this ratio, like base and acid concentration, if it's 1, like equal, then the ratio will be 1. So log 1 will be equal to, log 1 is 0. Correct? Log 1 is 0. So at that time you can get pH is equal to pKa. Correct? pH is equal to pKa. So that will not be changed because pKa is always a constant. So pKa will not be changed. So at that time pH is also not be changed, right? So that's our purpose. Buffer the purpose is pH have not be changed. So that's why whenever we are taking the buffer, initially we have to start with a like equal amount of base and acid amount. After that, like if when you are adding acid or buffer, it's within the range of like buffer capacity, they will maintain this ratio, right? That we already studied. Like the ratio will be very low. So at that time you got a constant pH. Correct? So that's all about the buffer. Alright, that's all about today's video. If you have any doubt, please drop a comment below. And yeah, definitely if you found this video helpful, please do like and share and support. And don't forget to subscribe Sanu's Chem Corner. Bye. Thanks for watching.